Welcome everybody to the SMRI seminar. And it's a great pleasure to host today Jose Carrillo from Oxford University. Jose received his PhD in 1996, University of Granada in Spain. After this, he had a postdoc at Texas. And after this, I think he received the first position in Barcelona. He stayed more than 10 years. And then he became professor at the Imperial College in London. And since how many 3 years?
Yes, since the
3
beginning.
years, who are now professor at Oxford University and recently received the prestigious ERC grant. And so it's a great pleasure to host you here and to speak about non-local aggregation-diffusion equations, fast diffusion, and partial concentration. Please start.
Thank you very much for the introduction, Daniel. It's a pleasure to be here. These 2 weeks at the Institute have been great. Okay, so today I want to give you some overview on some particular aspects of aggregation-diffusion equations. So I will not go too much in details on the proofs, but I will give you at least an idea of why we are interested in that particular second part of the title, fast diffusion and partial concentration. But to get there, let me just first motivate the questions and the main issues related to that problem. Okay, so let me start by discussing the minimization problem, from where it comes, this kind of question. So the minimization problem, from where everything comes from and all the models are based on. So let's assume that we have m particles. The particles are denoted by xi. Xi is just the position of the particle in Rd. And you're looking at the evolution in time of those particles that are subject to forces that are given by an interaction potential. That here I'm denoting by U. Okay, U is an interaction potential that may be singular at the origin, but that's why I'm assuming, just to simplify your life, let's assume that U is a radial function. And the only possible singularity is at the origin. So think about, for instance, the Newtonian potential for attraction or repulsion of particles. And here I'm writing the first order dynamics. So I'm writing the time derivative of xi equals the sum of the forces, because I'm thinking like Newton's law. So I'm assuming a second order differential equation system, if you want, where I have damping and I neglect the inertial term. I assume that the inertial term is negligible with respect to the rest. That's why I have first order dynamics. So the second time derivative is just neglected. So that's why you get into this kind of equation, xi dot, the time derivative of xi equals the sum of forces. Say that the particle Sj is producing a force of particle xi given by gradient u of xi minus xj, and you add them with certain weights that you can think about it as masses. I mean, this is in principle, independently of any physics model, I can assume that we have that kind of interaction. But what I'm interested in is to look at continuum versions of these particle dynamics. So typically how you look at, how you develop the model out of the particle dynamics. So in this kind of in this simple sample, you can do it just by mimicking how you are computing here the velocity field of each of the particles. So how do we do that? Let's introduce rho Tx as the notation for the density of particles at time t. We can think about that as the mass density of particles that you find at time t. And then related to the, let's see, here's chart. So related to the particle system, you could think about, this is how it works. I just push, or the, yeah. No. Doesn't work like that. It's a machine kind of thing. Okay, forget it. I write it here. No, I don't need to. Yeah, that's fine. So you define mu n is what is called the empirical measure associated to the particles. You can think about for all the position of the particles xi, you get a probability measure that gives you that is at position xi or not. That's what is called the Dirac delta, the position xi of t. And you sum all these Dirac deltas with this strength. You can call this what is usually called the empirical measure associated to the dynamical system. And then you can think also in terms of looking at the limit n to infinity in order to derive the model at the continuous level. And somehow, if you want here, what I'm just doing is mimicking how I compute here the velocity field. I'm saying that each infinitesimal part of the mass, rho at location y, produces you a force at location x, which is given by minus the gradient of ux minus y. And then I sum all of them, meaning an integrate. Okay? More rigorously, you could think about, as I said, passing to the limit n to infinity on this empirical measure and show that rho satisfies certain PD. This is what is usually called the mean field limit. Okay? Great. So in any way, one way or another, just by formally copying the formula of the velocity field, you could think that the kind of continuum model that you expect for the continuum density rho is going to be something of that form. It's going to be a continuity equation for the density of particles. This means the partial derivative with respect to t of rho plus divergence of rho times the velocity field, where the velocity field is related to rho itself by doing the convolution with minus gradient. Okay? Good. So this is like the basic model that we usually refer in the case in which U is an attractive potential. That's why it receives the name of aggregation equation, because all the particles will be attracting each other. But I mean, you could think about the potential as attractive repulsive, or repulsive in the short distance and attractive in the long distance. And then, yes, you keep just the same name of an aggregation equation, but it's not that it could lead to aggregation. Great. So what I wanted to mention is about other models which are related to this one, which is what I usually refer as the aggregation-diffusion equations. That's probably better. Which then they are of the same form. They are continuity equations. So maybe we can just write here the PDE. And the velocity field here has two parts. The one that I just mentioned to you in the previous slide, minus the gradient now of a nonlinear function of the density that I call P. Okay, why that? You can think about these models. I mean, first of all, why I call it now aggregation diffusion, because if you just insert this guy here and you develop the two terms, you will get the same term as I had before, plus now the Laplacian of P of rho. So what you get is a diffusion equation, non-linear degenerate diffusion equation, coming from that term. Okay, but this is now completely local with respect to that due to the convolution we usually refer to it as a non-local term. Why there is some connection between the two? So the idea is simple. So let's assume that you have a potential u that and think about it that depends only on the radius, and think about the potential that has that shape. So is with the signs that I chose, if the radial potential has the shape, whenever the potential as a function of the radius is decreasing, is repelling. The particles at that distance, they will repelling each other. While if it's increasing, the particles at that distance, they will be attracting each other. So what it means is that this potential is short distance, I mean, is repelling at short distances and attracting at longer distances. And you can think of a very strong repulsion at zero model, for instance, by making these more and more singular in some way. What do I mean by that? You could think that essentially your potential looks like a Dirac zero plus, again, let me call it U tilde, the attractive part. Okay? I mean, some sense. And if you do that, when you plug it in the equation that I have before, I mean, if you plug it in that term, so minus u con both rho will become Of course, you cannot do the gradient of a Dirac delta, but you will put it on the density, assuming that the density is better, I mean it's regular. So you will get minus gradient of rho, minus the gradient of u tilde from both rho. And essentially, let's say that it will give you this equation, putting a tilde there, okay? With the choice of P of rho equals rho. Now with that choice, that term becomes divergence of rho, gradient of rho, so it's like Laplacian of rho squared modulo. So still it's a nonlinear diffusion. Okay, I'm just gonna get rid of the tildes, simplify the notation for the rest. And that's why I'm considering this larger set of equations. So let's say that then we are modeling attraction known locally by the potential U and repulsion by the local term modeled by that nonlinear diffusion. And you can think about other ways instead of doing that approximation to get other powers or other nonlinear functions. Pure rho, people have looked at that. So that's why I'm writing a more general PDE. So that's what I was saying just now. So the main question I want to address is if repulsion is modeled by the nonlinear diffusion and the attraction, as I said, by the non-local term, by the interaction potential, when does a balance between the attraction and repulsion between these two competing mechanisms happen? So let's try to analyze that. There are two main tools that are going to be important to be used. On one hand, the fact that there is a Lyapunov functional. And on the other hand, that Lyapunov functional doesn't exist by causality, but it's important because, in fact, the equation, you can see it as a gradient flow of that energy function in a suitable method. I'm not going to discuss that much the gradient flow structure, the rigorous part of how to write that equation as a gradient flow. But the Lyapunov function can be discussed very easily in terms of just formal computations. So the functional, in principle, is a functional defined on probability, let's say mass densities. So nonlinear, so non-negative functions, which are interval in the whole RD. And the first part here is just the total potential energy generated by the density of particles. Why? Because you can think about U convolved with rho as the potential generated by the density rho, and you're multiplying by rho again, so you compute the total potential energy. I put the 1/2 just for simplicity to connect well with the PD. And then the second part, the blue term, will be obviously related to the nonlinear diffusion part if you choose the phi in the right way. So forget about what I'm saying here at the moment, but just that it's explaining in some sense the gradient flow structure of that equation. That is something that was introduced for the porous medium equation by Felix Otto many years ago. And for this particular kind of problems, we look at it with Robert McCann and Céline Villani also years ago. Anyhow, why you can see that it has some flavor of a gradient flow? Because the equation can be written in this form. In fact, the equation there, you can write it, the velocity field in the equation is given by minus the gradient of the variation of that energy with respect to it. What it means, this variation? It means that you are taking variations of the energy in the space of L1 functions with a given mass. Let's assume that the mass is 1. Let's assume that is 1, and then we are working with probability densities. Because you can always normalize. That's easy. Just change by constants your problem. So then you just need to do variations of these that conserves the mass and the non-negativity of the function rho. And if you do that, you realize that, in fact, this equation can be written in that way, can be written in this way, where the variation, if you compute it, is given by that formula here. It's given by U of rho plus phi prime of rho. And now you choose the phi related to P. So in fact, P prime of rho has to be the second derivative of phi with respect to rho. And if you do so, then you see that precisely what you have here is U of rho plus the corresponding phi prime of rho. So when you compute the time derivative of this, in fact, you realize that you can iterate by parts and get this formula here. So in fact, this computation is just one step if you want. We can just do it here. So first of all, that this is the same as minus u convolve rho gradient minus gradient of phi prime of rho. Okay. That's what is written there. And once you realize about that, what you can do is that the time derivative of the free energy functional rho t is given by, formally will be given by d rho dt times the variation. So I'm going to just write times the variation. That's the simplest way to see it. And now you just substitute the equation and iterate by parts once. And you can do that. Okay, substitute the equation. And you will have this with the choice I have done there. And then if you iterate by parts once, you will get minus rho, the gradient of the variation square. So formally, that is a good Lyapunov function. And in fact, I'm telling you that it's more than a Lyapunov functional. It's the Lyapunov functional that defines the evolution, because this is a gradient flow in some sense. You can already see that it's a kind of gradient flow because the velocity field is minus the gradient of something. But that's not enough. But that's for another day. Okay, anyhow. So now I can explain better what do I mean by a balance between attraction and repulsion. What I am interested in is to find conditions for local minimizers, systems of local minimizers, or global minimizers of this free energy function. Because local minimizers or global minimizers are expected to be among the stable steady states of your evolution. Okay? So let me just mention that that kind of question has been studied quite a lot in very classical setting for in crystallization in statistical mechanics. These typically correspond to the case of Lennard-Jones potentials, which are very singular, for which this doesn't really make sense because they are so singular that they're not locally iterable, and then this double integral doesn't make sense for probability densities. So nevertheless, what they did in those works is to study it in the set of sum of Diracs, and there are plenty of interesting results in there. Probably the closest thing to what I'm saying today is the model by in which you use as U the Newtonian potential, either attractive or repulsive. And for instance, the attractive case, which is the most interesting for us today, is a model that appears in mathematical biology, and it goes with the name of Keller-Siegel model, that it tries to model the movement of cells that are subject to chemical cues, although it appears also in astrophysics. And there are other applications that I'm listing here. For instance, you can also study fractional diffusion when you use more singular than Newtonian potentials up to modulus of x to the minus dimension. And also is related to the eigenvalue distributions of random matrices for suitable choices of the U. And so there are some particular instances of that question that have been studied quite a lot. Okay, but not what I'm discussing today is what is the general relation between them. So let me then change gears and then focus on a particular case of that problem. Let's do it at least in the case of power loss potentials. Okay? So what I mean is that let's do it for everything that is homogeneous. Let's assume that the nonlinear diffusion is homogeneous of exponent n. And let's assume that the potential U is just a radial potential, also homogeneous of power k. The k there is between minus dimension and dimension, if you want. One can go larger than dimension, but not below minus dimension, because then is the limit of the local integrability here. With that notation, I can use k equals 0, but this is just a notation to say that when k equals 0, I take the log. In this way, I always get the Newtonian potential even in 2 dimensions, if you want. And the chi here is just a constant to take into account the relative strength between the attractive part and the repulsive part. And let's assume that we, in some cases, I will normalize rho to have mass 1 or not, but they always have a fixed mass because you have conservation of mass in these evolutions because it's always a divergence. And typically the behavior at infinity is good enough that you don't have problems on conservation of mass. At least formally it's always conservative. Okay, so let's see. In this particular case, can we distinguish the different cases? There is very nice computation that is not written on the slides, but it's worth it to mention, which is the following. Let me just write here the energy. That's the energy. And what I'm going to do is just simply to study a little bit the landscape of the energy by doing dilations of a given density. I give myself a profile of a density, and then I just scale it. Okay? So say that I do lambda x, lambda to the dimension, and I call this rho lambda. So rho is given. Give me any L1 non-negative function with a given mass. I just do dilations with lambda positive of it. And I look at the value of f of rho lambda. Okay? Since everything is homogeneous here, the u is a modulus of x to the k, and the nonlinear diffusion is homogeneous, you can do the computations and see how it depends on lambda. Okay? And you can see that both terms are homogeneous, and the homogeneity of each term depends on here on k and here on m. Okay? So if you do that algebra, you realize that you may identify at least formally different cases. The case in which m is larger than 1 minus k over dimension corresponds to the fact that when you do this scaling, is more energetically favorable to spread than to concentrate. What do I mean? If you concentrate, your energy increases. If you spread it, your energy decreases. Since you are minimizing, then it makes more sense for looking, you're looking for minimizers to spread the density. Okay? So that's why I call it diffusion dominated regime, because somehow when n is larger than that value, then if you are going to minimize, it's better not to concentrate the density. So then in that case, you would expect to have, in fact, in that situation, you would expect to have global solutions, and you would expect also to have some non-trivial behavior as t goes to infinity, depending on the ranges. I'll come back to that later. I'm just here referring to two particular papers in that direction, in that regime. If you are in the opposite regime, when n is less than 1 minus k over d, so what you expect is the opposite, because you look at the homogeneities, when you concentrate, your energy decreases. And in fact, you can prove that in many of these regimes, and I will come back to that later, the energy can be even not bounded below. It can go to minus infinity simply. So then, in that case, you would not expect to have global minimizers. But if the free energy is not bounded below, then what you can prove is in some cases you have what is called finite time concentration, or typically is called blow up in this business. Blow up in the sense that the densities, the evolution of the problem will lead you typically from something that is an L1 function to concentrate somewhere and leading to be an L1 function. Okay, that's what I call as what I refer as a concentration. And again, here I'm referring to some particular papers in this direction. And in fact, I want to mention this paper is by Jianguo Liu, Li Chen, and Jinghua Wang that is present in the audience. So they did a very nice work on that case. So, and what happens when m is equal to 1 minus k over d? That is where both terms in the free energy, they have the same homogeneity. So they compete at equal foot. And in fact, what happens, and that's quite interesting in that particular regime, what happens is that chi now plays a role. Remember chi, I forgot to put it here. In fact, well, no, I didn't forget it because it was in the definition of U. But remember that U is chi modulus of x to the k divided by k. So chi doesn't play any role in the other regimes, but in the fair competition case, when they are both equal homogeneous, then chi plays a role. And it was known, at least in one particular case, in the case in which you had the Newtonian potential. I did a work with Blanchet and Lorenzo years ago for the Newtonian potential, and which corresponds to k equals d minus 2, 2 minus d with this notation. K equals 2 minus d correspond to the Newtonian. And in that case, with the corresponding m, we saw that there is a critical value of chi separating the different behaviors. In fact, there is a critical value of chi such that if chi is larger than chi c, you behave like in this case, you have finite time blow up. While if chi is less than chi c, you behave like in this case, that you have global solutions. The asymptotic behavior is somehow a bit different between that case and the chi less than chi c of that case, but I will explain that later if I have time. And finally, the chi equals chi c is a very interesting problem too. It seems very particular and very specific, but it's not. It's very interesting because it's related, in fact, to functional inequalities, which are important in analysis. So in fact, this is the next point I want to explain you, how we discover about all the, rigorously, how do you deal with all of these cases. So let me explain you the fair competition regime first, because it's where you see how things develop. So remember, fair competition refers to the case in which n is equals 1 minus k over d. I write in the first line. In the second line, I'm just telling you that the function is homogeneous for respect to dilations. The homogeneity is lambda to the minus k. Of course, this tells you already one thing. If there are stationary solutions, all of them, they must have zero energy. Because if you have a steady state, then when you rescale it, then you should have global minimizers. Sorry, you have global minimizers. Then when you rescale, it should give you the same values. So the only possibility that gives you the same values that lambda for any lambda is that the free energy of the global minimizer is zero. Okay. So in fact, it's also true for a stationary state, but this deserves a different discussion. A particular case has received lots of attention in the literature and corresponds to this classical Keller-Siegel model for chemotaxis that I was mentioning at the beginning in the introduction. It corresponds to the case in which k is equal to 0 in so the log kernel and diffusion linear m equals 1. In that case, this I didn't mention what happens when m equals 1 here. So when m is equals 1, that should be substituted by the Boltzmann entropy, like integral of rho of rho. That's for m equals 1. You can see that is the limit of this one. When m goes to 1, you just subtract conveniently a constant. So the case k equals 0 and m equals 1 corresponds to the classical Keller-Siegel model in 2 dimensions. For instance, and in 1 dimension is a modified Keller-Siegel. It has been studied by many people. I'm just listing part of the people that have worked on that. In that particular case, it was already known that there is a critical value of chi. In particular, the paper I just mentioned of Blanchet, Lorenzo, and myself, we did it for the Newtonian in any dimension, in particular in dimension 2, that will correspond to the 2D case of that problem. And what I mean about the critical value is that there is a critical chi c, such that, in fact, if chi is larger than chi c, the free energy is not bounded below, and we just expect this finite time blow up for the evolution problem. If chi is less than chi c, there are no stationary states, but solutions exist globally, and they converge to a self-similar profile. And for chi equals chi c, that's the interesting case again. As I mentioned before, in that case, you can prove that there are infinitely many stationary states. And let's see a bit more in detail that case. So in fact, it is related to a super classical inequality in analysis, which is called the Hardy-Lidl-Sobolev inequality. The Hardy-Lidl-Sobolev inequality is an inequality that was derived with optimal constants in a famous paper of Elliott Lieb at the beginning of the 80s in Annals, in which he proves that you can bound the double convolution of a function f with a kernel, what he usually refers as the risk kernel of power k, when k is in between minus dimension and 0. Here I'm always working with k negative for the time being. If k is between minus dimension and 0, is you have the double convolution with the singular kernel, and you can bound this in terms, the standard HLS inequality, you bound it in terms of the LP of f with that exponent, and he was able to find the critical constants and the optimal constants of that. That's the famous paper of Lieb. What I'm telling you is that here there is a very related inequality that helps you in finding the critical parameter from this, which is a slight variation of the HLS inequality. That's why I call it a variant HLS somewhere. And the variant of the HLS is that once you apply the standard HLS inequality and you get here a constant multiplied by the LP norm with that value of P squared, you interpolate that value of LP between L1 and Lm, because that value of P is in between 1 and m. And you get this estimate. And why I do that, why I interpolate between the L1 and the Lm norm, because in this way I make appear the density, the L1 norm of the density in my application that I know is given, is a constant. And it will help me also to estimate this term in terms of that term, which is exactly the Lm norm to the L. Okay? So there are two reasons why I do that. So that's the inequality you get, but it's more. That inequality you can also study as a function inequality. You can ask yourself, what is the best constant in the function inequality and what are the optimizers in the inequality? And what you can prove is that the best constant of this inequality defines for you the critical value of chi. They are intimately related. They are one-to-one. It's just an expression, one in between the other. I don't know, I don't have it written in the slide, but believe me, it's just an algebraic expression between the optimal constant and the critical chi. Because this allows you to control from below this functional and then prove that when chi is less or equal than chi c, this function is bounded. And also for chi equals chi c, they coincide with this gives you an exact inequality that tells you that the free energy is always larger or equal than zero. It's more than that, as I'm saying in this line, in the critical chi c, the optimizers of this variant of the HLS inequality are the global minimizers of the free energy. So that's why you have this if and only if. The free energy is zero, in fact, if and only if is an optimizer of the HLS inequality. So the message to remember here is that when k is between minus b and 0, then the critical value chi is determined by this functional inequality, this variant of the HLS. Good. And let me just say then that that in principle was known only for k equals 0, m equals 1 in 2 dimensions. Once you realize about the corresponding inequality, this applies to all k's between minus dimension and 0 and the corresponding m in the fair competition regime. Okay, so let me summarize in a figure. And here I'm doing a figure with the k in the abscissas and m here. So what I discussed in the previous slide was k between minus dimension and 0. I was telling you that there is this line, which is m equals 1 minus k over d, that corresponds to the fair competition regime. In this line is where I have this chi-critical phenomena happening. The diffusion dominated when you expect the evolution to spread always, and spread is more favorable energetically. It corresponds to m larger than 1 minus k over d. The attraction dominated below. In this case, I will not discuss too much today on that case, but let me just mention to you that in that case, what you can prove is that independently of the value of chi, now the chi doesn't play any role, independently of the value of chi, there is always a global minimizer of the systems modulo translations, which is a steady state, which is complex-apoptic. So the diffusion dominates in the sense that it doesn't allow you for concentrations, but asymptotically, in fact, what you expect is convergence towards that steady state. This has been proven only in particular cases, but you expect the result to be true in the whole range, but only has been proven for technical reasons in particular cases. So the particular cases have been proven in all the yellow part for K negative, except in this range over here, that corresponds to very singular potentials that in the language of fractional diffusion, that there are some people here interested in fractional diffusion, it means that you are very close to the limit of the minus dimension in the fractional scope. Okay, so very good. So we clarified somehow in that series of papers that probably this picture corresponds to a paper of with Franca Hoffmann, Eduardo Mainini, and Bruno Bolzone some years ago. Franca was a PhD student of mine that's now in Caltech. And we clarify all of this. But what happens in this range when the K is positive? What happens when I take an attractive potential, but now it's not singular anymore? It's just a modulus of x to the power k with k positive. Do we have still that the homogeneity plays a role in some sense? And what is known here? So that's essentially the second part of my talk, that in which I will just explain you very few details. And let me just tell you that one thing that we realized at the beginning is that the situation is going to be different because the homogeneity doesn't play an important role, in fact. So again, the question is the diffusion, in fact, in the diffusion dominated case, at least, the diffusion will win, but in which sense and when? So that's, you will see what do I mean on this. First of all, we realize that, again, there is a functional inequality that plays a role. The functional inequality is what is called a reverse HLS inequality. And the idea is somehow simple. So if now we take K positive, somehow we go to the range in which M is less than 1. So we see already here that the role of the two functionals, they change sign, both of them. This changing sign, but this one too. So it's not so unnatural to think, is there a function inequality similar to what we had before, but in the other direction? And this is what we call reverse HLS inequality. And in fact, in the literature analysis, you have reverse Helder, reverse other things. So now I'm using the notation probably here of LM for M less than 1. It's just simply a notation to say that the integral rho to the M is finite. I'm not claiming it's a banal space. It's for me to simplify my notation. Okay? And what it means, a reverse HLS inequality, it means that now you want to control the integral rho to the M to certain power multiplied by the integral of rho to certain power by that kind of moment. I would call it moment because it looks more like a relative kind of moment. Modulus of x minus y to the k, rho x rho. So is it true that we have an inequality of that type? And can we prove that in some range of M and K. So in fact, you can. And the interesting thing is that the range in which that kind of inequality is true, we prove it, that is, if and only if M is larger than D over D plus K, that has nothing to do with, in principle, 1 minus D over K. Okay? And it's an if and only if, the inequality. And I will tell you a bit more in the next slide. So moreover, in some cases, under certain assumptions that are written there, don't forget about reading them in detail. I will have a figure now to explain it to you. Under certain assumption on the exponents, then the minimizer exists in L1 with integral of rho to the n finite, and is radial non-negative optimizer. I'll tell you in a sec, in this figure, what I mean by that. This is the curve here, the curve M equals D over D plus K. For you to see the relation with the previous straight line that I had, M equals 1 minus K over D, that is tangent to that curve at K equals 0. Okay, but it lies all below. So what we prove, in fact, is even more, that free energy, because of the reverse HLS inequality, is bounded below if and only if you are above this curve. And in fact, on the curve are below, the free energy is not bounded below. So what happens is that, independently of the homogeneity or not, the free energy becomes unbounded from below. So then the homogeneity doesn't play any role anymore, because you could have densities with value minus infinity. If you scale them, they are all minus infinity. So that's what is going on. So the free energy becomes unbounded from below, starting on that curve, M equals D over D plus K. Because of the reverse HLS inequality, as I said, we know that the functional is bounded below above that. Let me mention that this red curve here, which is M equals 2D over 2D plus K, it was the only known case before we arrived to this question of reverse HLS inequalities. There was one specific relation between M and K in the literature, proven by Doe and Zhou, and then improved by Engo and Nguyen, that they got that reverse HLS inequality with sharp constants in that line. But now what we prove is that it's true for all the regime. Okay, what else? The well, if we are in all the part of this region too, that is in dark gray. So in the gray part, these are the conditions under which we can prove that the minimizer of the free energy, which coincide with the optimizers of the reverse HLS inequality, is an L1 function. But here, even if it's bounded below, in all the white part, we don't know, at that point, we didn't know that the minimizer is an L1 function. But that's the next surprise here. Let me just mention that 3 is boring. There is global minimizers, so I consider it a boring case, and radial, so it's easy to prove it. But let's focus on the white part here. So what happens there? So in fact, the way we prove that in the whole range above the curve, we could find a global minimizer of the free energy if we extend the free energy by Diracs at 0. What I mean is that you look for a minimizer in the set of L1 functions plus possibly a Dirac at 0. Okay? So if you minimize in that relaxed variational problem, we were able to show that in fact you have a global minimizer which consists of a part that is L1 and a Dirac at the origin with certain mass. And what we were able to show in fact is that the mass is 0 in the gray region. The question is, so because this is for some M, that could be 0, so then you don't have any singularity there. But the question is, does the concentration really happen or not? In the sense that, do we have a range of M for which this M is a star is positive or not? So in fact, in the first paper, we just gave negative answers to that. We just gave regions in which M is a star is always 0. So in fact, concentration for minimizers, I wouldn't be talking about that if it were not true. So finally, we have been able to prove it. But let me just go to, let's say I'm going to skip all the proof, but I'm going to just tell you the result. Okay, fantastic. So we were able to prove it for a particular K. Why for a particular K? In principle, we tried many times to prove nearby the curve in which the free energy becomes unbounded below. Do we have concentration nearby? In general, for any K, but we didn't succeed. So it said, okay, let's be a bit less ambitious. Let's take a particular value of K. The easiest value of K equals 2, probably. But no, that is not good enough because it's always in the good range. Let's go to K equals 4. Why K equals 4? Because if I have modulus of X minus Y to the 4, I can expand in terms of lower exponents. And not only that, since I'm looking for radial minimizers, because you can prove that all minimizers, global minimizers have to be radial. That's easy to prove. Then all the odd moments disappears by symmetry. So then when you expand the power 4, you end up only with modulus of X to the 4, modulus of X minus Y to the square, and modulus of Y to the 4. And then you can express your free energy, your convolution part in terms of moments, order 2 and 4, essentially. So in that case, we are able to give the existence of a critical M in which you start to have a concentration. So probably just, I go back to the figure here. Okay, so I'm taking K equals 4, let's say it's here. What I'm telling you is that I can go with this line, and in this line, there is an M in between, such that if M is larger than that, there is no concentration. And if M is less than that, you have a mass in the direct that is positive. Okay? So to be precise, for K equals 4, if M is between D over D plus 4 and D over D plus 2, you have a minimizer such that if the dimension is less equal than 5, the M star is 0. But as soon as dimension is larger or equal than 6, you have this critical M such that if you are below, then your mass is it's known, explicit, and it's positive. And if D is larger or equal than 6, and you are above that critical value, the M star is 0. So you have either a critical value or making a difference between concentration and non-concentration. So that's final result I wanted to mention. And just to say that right now, just the conclusions. So I hope to have convinced you that this problem of the aggregation diffusion, even with homogeneous pressure and kernel, is quite rich. In the case of the fair competition regime in the exponents, you have a dichotomy when quite similar to the classical Keller-Siegel when you are dealing with singular kernels. The behavior when you go to the fast diffusion case, when M is less than 1, in the fair competition regime doesn't make any sense because the homogeneity doesn't play a role. But in fact, we discovered these reverse HLS inequalities that characterize somehow the diffusion dominated regime. And finally, the concentration phenomena that somehow is surprising, that you need to put a direct to have a global minimizer at 0, does happen, but we don't have a full characterization. We have it only for particular cases. And I just want to thank my collaborators in some of the papers I explained today, especially the part of the fast diffusion is in the last, in these 2 papers, in the 3rd and the 4th. And thank you for your attention.
Thank you, Jose. Are there any questions or remarks?
Jose, you made a very interesting comment about the best constant in the Carrillo.
The variant of the HLS, yeah?
Yes, and there is a whole, say, industry of finding the optimal constants by using, say, Bellman equation and so on. Is it related? Can you apply it to can you have a connection to the PDE of this or with non-local kernel in other cases?
I mean, proving optimal constants for functional inequalities via evolutions, via flows, is something that started to be on fashion after precisely the paper that Carlen, Loss, and myself wrote on the HLS inequality. People have looked at that for in different ways. This variant of the HLS inequality is one of them. There are even for Sobolev, some particular versions of Carrillo, Nirenberg, Sobolev. People have looked at that. So yes, so people are looking at using, in fact, evolutions to prove the existence of the characterization of optimal constants. So you can use it in that way also. I use it in one direction, using the functional inequality on my favor to study the evolution. But you can also use it in the other way, proving the functional inequality by the evolution.
Thanks.
Is for the reverse HLS inequality the optimal constant? No, not.
Yes, I will.
And is it attained only in the full space?
It depends on what you mean by no. Is it
explicit? Yes.
No. It's just it's indirect in this case. Even in do we know it in some particular case? That's a good question. I don't remember if in the case of Doe and Joe, probably yes. In that particular curve, there is some of them that is fully explicit.
Okay. Then let's thank the speaker again.